Hello and welcome to my poster. This research is being presented at the Undergraduate Research Conference at Texas Tech University for the Department of Chemistry and Biochemistry, along with my co-authors URC and my mentor Dr. Gerardo Gámez. This presentation is about compressed sensing single-pixel imaging for GDOES elemental mapping. GDOES is an analysis method in which we can determine the elemental composition of a solid sample. It provides great quantitative analysis as it is fast and has good depth resolution, but under normal conditions it lacks lateral resolution. However, as shown in Figure 1, we see that when operating at higher pressure and pulse power, this can be overcome. This is often demonstrated with a 2D array detector, allowing high throughput elemental mapping. However, 2D detectors have a decreased availability due to their expensiveness. GDOES EM can also be achieved with a 1D detector via pixel-by-pixel imaging, but this requires a significantly larger amount of time. So this is where compressed sensing comes into play. Compressed sensing consists of group sampling of random pixels, selected randomly to create incoherence and solving for the sparsest solution. As shown in Figure 2, a complex signal first plotted as a function of time can be plotted in the frequency domain, in which we can find sparsity. By doing group sampling, we decrease the number of required measurements while still being able to reconstruct an image with equal resolution. Therefore, applying this concept to a 1D detection system can be very beneficial. A common CS single-pixel imaging system is shown in Figure 3. We start with the light that goes through the pattern mask displayed by the digital micromirror device, or DMD. This mask blocks or transmits the randomly selected pixel groups, and then a wavelength selection device selects and transmits the selected length depending on the sample. Then the 1D detector collects the signal. In Figure 4, we have the system schematic utilized for the imaging system. The light from the glow discharge chamber is reflected and focused into the DMD. The DMD projects the different random visual masks, which selects pixels by reflecting them into the light path. Then the light goes through the monochromator and the PMT, which is our 1D detector. Then a low noise amplifier and into a filter to reduce the noise in the signal. And then the signal is collected by MIDAC. In this project, we use 4 different matrix densities: 512, 1024, 2048, and 4096. These refer to the number of pixels that are grouped and transmit simultaneously from the area of 256 by 256 pixels. Then we utilize different compression factors, which refer to the percentage of measurements taken compared to the regular pixel-by-pixel rastering, which is a total of 65,536 pixels. The signal obtained is sparsified using discrete cosine transform, or DCT, and the discrete wavelet transform, or DWT. And then we use 2 different reconstruction algorithms: the gradient projection for sparse reconstruction, or GPSR, and 2-step iterative shrinking thresholding algorithm for linear inverse problems, or TWIST. The fidelity of the reconstructed image is compared using the peak signal-to-noise ratio, or PSNR. We also perform computer simulations in which we reconstruct an image and test how changing noise levels affects the fidelity of the reconstruction. In this poster, we present simulations using the cameraman test image. We first select the desired image and multiply it by a matrix of zeros and ones to simulate the DMD masks. Then an SNR factor is added to the peaks to simulate the noise generated from a detector. For these simulations, we use the same 4 matrix densities as before and the same reconstruction algorithms. The fidelity of the images reconstructed from the simulations was measured using PSNR and the Structural Similarity Index. Another important factor is the experimental timing. As we can see in Figure 6, the DMD displays the random mask patterns at a period of 100 milliseconds and a duty cycle of 66%. Therefore, the RFGD pulse frequency needs to match the matrix frequency and is set at a frequency of 1 kHz and a 2% duty cycle. In Figure 6, we can see a picture of the sample used for this experiment, which consists of the 3 copper dots inserted into a steel piece. The copper dots are copper 1, which emits a wavelength of 510.5 nanometers. Moreover, in Figure 7, we have a reconstructed image using the 512 matrix density and the DWT and twist reconstruction algorithm. This image lets us see how compression factors affect the resolution of our image. As we use bigger compression factors, the resolution increases, but after 30% there is not a very noticeable increase. As mentioned before, the image fidelity is measured using the peak signal-to-noise ratio. The PSNR equation compares intensity values of the reconstructed image and the reference image pixel by pixel. For the experimental results, we utilized the 100% compression factor as a reference image, and for the simulations, we used the original cameraman image. On the other hand, we can also calculate fidelity using the Structural Similarity Index, or SSIM, which instead of calculating absolute errors, it is based on the idea that the pixels have strong interdependencies, especially when they are spatially close. Both the PSNR formula and the SSIM formula are found in the third column of this poster. For the copper dot sample, each matrix density had 2 sets of data taken at 100%. From each 100% compression factor, we took 2 sets of compression factors, one starting from the beginning and then one starting from the middle. Each compression factor sets consist of 10%, 20%, 30%, 40%, and 50% compressions. Therefore, the error bars from the PSNR plots were obtained by calculating the standard deviation of the 4 different results of each compression factor. For the computer simulations, we wanted to test how different levels of detector noise would affect the quality of the reconstructed image. To do this, we used a function that adds white Gaussian noise to the signal before reconstruction, and we tested values of 30 SNR and 50 SNR. In Figure 8, we have a visual representation of how the 30 SNR and the 50 SNR detector noise affects the reconstructed image compared to the original image. In the simulations, we tested compression factors of 10%, 20%, 30%, 40%, and 100%, and we calculated PSNR values and SSIM values to see how the noise levels affect the image fidelity. Underneath Figure 8, we have the plots of all the matrix densities compared to the 2 level of noise applied and comparing PSNR values as well as SSIM values. We can see how there is a general trend of an increased fidelity with a higher compression factor. In conclusion, we have shown that GDOES elemental mapping compressed sensing single pixel imaging system is successful, with higher throughput than pixel by pixel rastering. We also see that PSNR values are higher with a smaller sampling matrix. PSNR values are also higher with increased percent sampling, but after 30% the improvement is less significant. Furthermore, the sparsifying basis and the reconstruction algorithms are similar at the 512 sampling matrix, but they differ more as we increase the sampling matrix. As for the computer simulations of the detector noise effect of 50 SNR, the sampling and reconstruction parameters variation reproduce PSNR trends as observed in the experiment, except for relative fidelity of DCT and GPSR. We can also conclude that since the 50 SNR is representative of experimental conditions, the detector noise dominates observed trends, and the SSIM values yield similar trends. In the future, we will work on computer simulations that can be done using a GDOES EM image to best represent the experiment. We will also test for different noise levels and noise types to compare Gaussian noise versus Poisson noise. We will also test different noise sources such as source noise. Thank you for your time, and if you have questions, feel free to email me to the email address located at the top of this poster. Thank you.